This is the second of 3 lectures from Chapter 9 on chemical bonding, and this lecture will focus on covalent bonding. So I introduced the idea of the Lewis theory, which simply uses dots to represent valence electrons. And we talked about making Lewis structures, showing ionic bonding. Well, this lecture is going to focus on drawing Lewis structures for covalently bonded compounds, which is a lot trickier. So just a reminder, covalent bond means that valence electrons have been shared rather than completely transferred between the two bonding atoms. So to show you kind of a picture of both of them, which I think is kind of cool, if you look at the right-hand side, it shows you ionic bonding, which completely transfers one valence electron from an atom to another one, generating a cation and an anion. Okay, and so strong electrostatic attraction between the oppositely charged ions. A covalent bond does not transfer any valence electrons, and it's mainly because both atoms in a covalent bond are nonmetals, and nonmetals don't tend to want to give up their electrons. They have relatively high ionization energies, and so they don't really want to give them up, so they end up sharing valence electrons, enough valence electrons so that both participating atoms end up with an octet of valence electrons. Okay, so just a little bit of convention. When you're drawing Lewis dot structures for covalent compounds, you'll run into quite frequently unpaired electron pairs. Those are called lone pairs or non-bonding pairs. When you're asked to draw a Lewis dot structure, you definitely want to show these lone pairs of electrons. They're important in future chemical reactions. All right, so covalent bonds, you can have a single, double, or triple covalent bond. So every single covalent bond is made up of 2 electrons, okay? So if 2 electrons are shared, that's called one bonding pair or a single bond. And in a Lewis dot structure, you can draw, instead of drawing a single bond as 2 electrons right next to each other, you can replace those 2 dots with a line. Okay, so that's perfectly fine in Lewis dot land. A double covalent bond is simply when 2 atoms share 4 electrons or 2 pairs of electrons. Okay, and it's written like this. Each bond has 2 electrons in it. So you have a total of 4 electrons. Oxygen is a really good example, molecular oxygen. Remember, oxygen is one of the diatomics. Because oxygen starts out by itself, it has 6 valence electrons. And so you can see simply from drawing the Lewis dot structure of the oxygen atom that oxygen would like 2 more valence electrons to give it a total of 8. And so by 2 oxygen atoms forming a covalent bond, they each end up with 8 valence electrons. Triple covalent bonds are when 6 valence electrons are shared between atoms. Okay, so you have 3, you can think, it's not really 3 single bonds, but you have 3 bonds that connect. Nitrogen, another diatomic, is a good example of a triple bond. Nitrogen atom on its own has 5 valence electrons. And so you can see by looking at it that nitrogen would like 3 more electrons in order to end up with a total of 8. So it gets those 3 extra electrons by covalently bonding with another nitrogen atom and making a triple bond. And in that case, both nitrogens end up with 8 valence. All right, so this is just the relationship between bond length and bond strength. The stronger a bond is, the shorter it is. okay? So I like to think of the two S's that go together. The stronger a bond is, the shorter it is. Stronger and shorter go together. And that's kind of makes sense, right? If you think of two things, if they have a very, very strong attraction, they're going to get pulled together more, and the distance between them will be shorter. So bond strength, hopefully this is kind of intuitive. A triple bond is stronger than a double bond, which is stronger than a single bond. And now looking at bond length, the shortest bond is the strongest one. So a triple bond, because there's such strong pull between the atoms, a triple bond is the shortest, okay? And a single bond is the longest. And one thing that's important to remember as we move along in this chapter is that anytime you break a bond, doesn't matter what type of bond it is, anytime you break a bond, that is an endothermic process, meaning you have to put in energy to break a bond, just like you have to exert energy to break anything. And conversely, making a bond is always exothermic. So when you make a bond, there's always a release of energy. And that's because as you make a bond, the system itself is going to a lower energy, and that extra energy is to be kicked out. This is the only calculation that you're going to have to do in this chapter. And what we're going to do, or I'm going to show you how to calculate the enthalpy of reaction. That's kind of, hopefully you remember a little bit about that from our thermochemistry chapter, using bond energies or bond enthalpies. And we learned in our thermochemistry chapter that you could calculate enthalpy of reaction using Hess's law. You could calculate it by adding up heats of formation. And in this case, we're going to calculate it using bond energies. So here's a typical bond energy chart. So when you're given a calculation to do, you'll get a chart like this. And it gives you how much energy is in each, I didn't line that up very well, in each type of bond. Be very careful when you're using these tables to pay attention. Is it a single bond, a double bond, a triple bond? They all have different energies, so be careful with that. Here is the formula we use for bond energies. So the total enthalpy of reaction is the sum of all of the bonds broken minus the sum of all of the bonds made. So when you're trying to add up bonds broken, you want to look to the reactant side. Okay, all the bonds are broken from the reactants. When you're looking at new bonds formed, you need to look to the product side of a reaction. So here's an example, and I've learned that students in Gen Chem don't understand this structure, so I apologize for writing it like that. I went into organic chemistry mode. And let me rewrite that. What I intend for that molecule to be is two carbons, triple bonded, each of them with a hydrogen atom. All right, so now here's a typical bond enthalpy problem. What you would do is you would start one column with bonds broken and another column with bonds made, and you would tally them up and then subtract bonds made from bonds broken to get the delta H value. So if you think you can tackle that, I will go ahead and try it on your own, but chances are, unless you have some experience in this already, you probably have no idea how to do it. So I will show you how on the next slide. Alrighty, so let's tally up our bonds broken, which means we need to look at the reactants. All right, so how can you tell if a bond is broken? Simply look at the bond. Here I'm looking at carbon-hydrogen bond, and see if you see it on the product side at all. There's no carbon-hydrogen bond in either of the products, so that bond has clearly been broken. How many carbon-hydrogen bonds have been broken? Be really careful here. We have that one. Here's another one. There are 2 carbon-hydrogen bonds in the same molecule. But the balanced equation shows there are 2 of these molecules. So 2 times 2 is 4 carbon-hydrogen bonds. And what else has been broken? Well, let's see. There's no carbon-carbon triple bond anywhere in the products. So we have 2 of those. So we have 2 carbon-carbon triple bonds. And the last thing we broke on the reactant side is an oxygen-oxygen bond, and there are 5 of those. So 5 oxygen double bond oxygen. Okay, let's go ahead and look at bonds made, which means you need to look on the product side. We have made carbon-oxygen bond, because that carbon double bond oxygen did not exist in the reactants. We've made 2 of them in each carbon dioxide molecule, but then we have 4 carbon dioxide molecules. So 2 times 4 is 8 carbon double bond oxygen bonds that we have made. We have also made, let's see, it's a hydrogen-oxygen bond, and there are 2 hydrogen-oxygen bonds on each water molecule, and then 2 water molecules. So 2 times 2 is 4 HO bonds. Now you look in the bond enthalpy table and you find the energy values for each of these, and you add them up. Remember, it's bonds broken minus bonds made. And we can see that the bond energy for a carbon-hydrogen single bond is 414. And we broke 4 of those, and so that contributes 1656 kilojoules to the bonds broken. Carbon-carbon triple bond is 837 kilojoules, and there are 2 of those. So 837 times 2, 1674 kilojoules. So we're going to end up adding those 2 together. And then we have 5 oxygen-oxygen double bonds. Alrighty, so the energy for an oxygen-oxygen double bond is 498. These are coming from the table on the last slide. And we have 5 oxygen-oxygen double bonds that we have broken. So we're going to multiply 498 times 5. And that is going to give us 2,500, 2490, I think, kilojoules. So if you tally up all of the bonds broken, and I'm out of room, so, and then you do the same thing for the bonds made, tally all those up together, and subtract bonds made from bonds broken. Did your math correct? You should end up with total reaction enthalpy of minus 2,428 kilojoules. So make yourself go through it so that you don't have any trivial misunderstanding. And from a conceptual point of view, you should be able to think through this problem and tell me what the answer is. So turn off the video for a minute and see if you're able to do that. So I'll give you a hint if you're struggling at all. So remember that bonds broken are always endothermic, okay? And the mathematical sign for endothermic processes are plus. Bonds made are always exothermic, which mathematical sign would be a minus. So if overall you have a reaction that is endothermic, what does that mean? That means that you either have more bonds broken than bonds made, or you have higher energy or stronger bonds broken than the energy of the bonds made. But in either case, what it means is that the bonds broken have dominated the energetics of a reaction. And because of that, let's go through these. Strong bonds break. Yeah, we just said that. Endothermic is ruling the day, which means we had to break strong bonds or else a lot of them. And weaker bonds form. Okay, that seems to kind of make sense. Let's look at why the other ones don't make sense. We already said that bonds breaking have to dominate. So weak bonds breaking, no. The bonds that break and those that form are approximately equal strength. That would give you, if that were the case, an enthalpy of reaction of 0. That would mean there's no net gain or loss if they were equal. And D is just flat out wrong. So the correct answer is A. All right, I'd also like to remind you for a moment of the 7 diatomics. They're going to get progressively more and more important to have memorized. And you can either remember that little goofy word we used to remember, which was Hofbrinkel, which kind of just a way to remember all of them. Okay. I'll give you another way to remember in a moment. But all of these are diatomic, which means in nature you only see them as pairs. So you don't see hydrogen by itself. It's always H2. Same with oxygen and all the rest of them. Also, what's kind of interesting is they exist as diatomics because they complete each other's outer shell. So hydrogen, they each need 1 electron because they only need 2 to complete the first outer energy level. Oxygen, each oxygen atom needs 2, so they share a double bond. Nitrogen, each nitrogen atom needs 3 more valence electrons to have an octet, so they share a triple bond. And this is, I think, the coolest way of remembering the diatomics. If you have a periodic table, you start with atomic number 1, which is hydrogen, and that is your first diatomic. Then you skip over to atomic number 7, because there are 7 diatomics, and that happens to be nitrogen, and then you draw a numeral 7, and now you have found all 7 diatomic molecules. All right, here we go. This is the tricky stuff, so if you need a break or you're sleepy, it may not be a good time to listen to this. Certainly the rest of 12, 11, and then a good chunk of the beginning of 12, 12, you have to know how to draw an accurate Lewis dot structure to be able to do the subsequent things you're going to learn, which includes the shape of molecules, their polarity, how they react chemically, etc. All right, so there are a series of 5 steps that I have found are fail-proof if you follow them. And it's going to be really tempting if you're an impatient type to kind of skip through them without making sure that you're really careful. And I will tell you, skip through them, you will make mistakes. So try to force yourself to go through all these. Step 1 is count up the total number of valence electrons for every atom in the molecule you're trying to draw a structure from. You have to remember the valence electrons for each atom in order to do this. Phosphorus is in group 5A, so it has 5 valence. Chlorine is in group 7A, so each of the 3 chlorines has 7 valence. So altogether, phosphorus trichloride has 26 valence electrons. The bottom line is you need to place however many total valence electrons there are in your Lewis dot structure. They all need to be accounted for. Just a little note here. If the molecule is an anion, so let's say there was a negative charge up here, that would mean there's 1 additional electron. And in this case, you would have 27 valence electrons. Now let's say that instead of an anion, let's imagine that we were dealing with a cation. That means that an electron has been removed, and you would have to subtract 1 from whatever your tally was. And in that case, you would have 25 valence electrons. All right, step 2. After you count total number of valence electrons, connect the central atom with a single bond to each of the other atoms. How do you know what atom is central? Well, honestly, 95% of the time, the first atom shown in a formula will be your central atom. There are some exceptions. For example, every now and then hydrogen will come first in a formula. Hydrogen can never be a central atom because it can only make one bond. So there are some exceptions, but that almost always works. All right, number 3. Fill or give the outer atoms an octet of electrons. Okay, so 2, 4, 6. And remember that each single bond represents 2 electrons. So you can see the chlorines now have an octet of electrons. Then know how to count how many electrons you've used so you know how many you have left to place. Count all the electrons you've used so far in this structure, and hopefully you come up that so far you have used 24 electrons, and you need to use 26 electrons, which means you have 2 more electrons to place. So the 4th step then is, if you have any electrons left over, at this point we have 2 left over, they go on the central atom. At this point, what you do is you look for an octet on every atom, because every atom wants to have an octet, of course, unless except hydrogen. So you check here, and you got really lucky. Each of the 4 has an octet of electrons, so you are done. So if you're lucky and it's a straightforward one, it's only 4 steps. But there will be quite a few of them that will require a 5th step. And here's that 5th step. Let's say that you run out of electrons and you notice that the central atom does not have an octet. So let's look at, if we were to start with this and we were to go through the steps. How many valence electrons? 1 plus 4 plus 5. So this compound has 10 valence electrons. So we're going to set it up with single bonds first, right? Okay, and then we're going to give the outer atoms an octet. And remember, hydrogen can only have a single bond. It only can hold 2 electrons, so you cannot add any more electrons to hydrogen. Now count how many electrons you have placed so far. 2, 4, 6, 8, 10. You have used all 10 electrons that you have. You don't have any more to place. But if you were to stop now, carbon does not have an octet. And that is not stable. Okay? So if you reach this point after the first 4 steps and your central atom does not have an octet, you need to start making multiple bonds. That means double bonds or triple bonds until your central atom has an octet. How do you make a double or triple bond? Well, for each double bond, you take 1 pair of non-bonding electrons on a terminal atom and use them to make a double bond, and of course then they go away. If you were to stop at this intermediate, let's write that for a minute. So you would have a double bond between carbon and nitrogen, and then you would have 2 lone pairs on nitrogen. Now if you check, carbon still does not have an octet. It has 2, 4, 6 electrons around it, so you have to make another multiple bond. You have to take yet another pair of lone pairs from the nitrogen and use them to make another bond, which now puts a triple bond between carbon and nitrogen. But now carbon has an octet. So this is your final Lewis dot structure. All right, so you are 2/3 the way through this lecture. It's a tough lecture, I know. So we're going to talk about something called formal charge. There are some cases when you're drawing Lewis dot structures, and it's in the more complicated molecules, where you'll end up with more than one Lewis structure that seems possible. If that's the case, you then need to use formal charges to determine the best one. There go my dogs. That's their way of playing. They're not fighting. So first of all, to let you know, formal charge is not a real charge. It is kind of a bookkeeping method that we use to decide on the best Lewis dot structure. All right, so here are the rules. It's kind of tricky, and the method I teach you, I think, is more straightforward than the textbook, but you're obviously welcome to use the textbook if my method seems confusing to you. So the bottom line is, to find a formal charge, you want the number of valence electrons that why does that keep happening? That an atom has on its own, if it were not in a molecule, minus the number of valence electrons that same atom has in a compound. Okay, so you want to see, did it hang on to the electrons it started with? Did it gain some? Did it lose some? And that's really what formal charge does. So let's look at an example. I think it's easiest to understand if you look at an example. Let's look at carbon dioxide and take one atom at a time. Oxygen starts with 6 valence electrons, right? When it's on its own as an element. In this particular compound, when you are counting valence electrons that belong to a certain atom, you count all of the lone pairs, and you count only one electron from each bond. So one's going to go to oxygen, the other electrons are going to go to carbon. So in this compound, oxygen has 2, 4, 5, 6 valence electrons. So it has 6 when it started, it has 6 in this compound, so the formal charge for that oxygen is 0. How about the carbon here? Well, carbon starts with 4 valence electrons, it's in group 4A, and in this compound it has 1, 2, 3, 4. You take 1 electron from each bond. 4 minus 4 is 0. So carbon also has a formal charge of 0. Let's look at a compound now that has atoms without formal charges of 0. Alrighty, looking at this oxygen. So oxygen, when it's on its own, has 6 valence electrons. In this compound, it has 2, 4, 6, 7. So this oxygen has a formal charge of -1 in this compound. The nitrogen normally has 5 valence electrons. Let's see how many it has in this compound. 2, 3, 4, 5. So the nitrogen has a 0 formal charge. This oxygen, again, starts with 6. How many does it have here? 2, 4, 5, 6. So the right-hand oxygen has a formal charge of 0. And so what you want to do with formal charge always, if you have multiple Lewis structures to pick from, is pick the Lewis structure that minimizes formal charge. It has a formal charge on the fewest atoms, and if atoms do have a formal charge, that it's the lowest value possible. If you are one to like formula, here is the official formula for formal charges, if you want to jot that down. All right, so let's look at a case where we would need to use formal charges. Here is a compound NCO. So if you were to go through the steps, which you may want to do, it'd be great practice, and make sure that you would possibly come up with these 3 possibilities. Let's look at these. These are called resonance structures. When you have Lewis dot structures that differ only in the placement of the electrons, and everything else is comparable, those are called resonance structures. Okay. Now, every atom has an octet in all of these resonance structures. So, which one do you use? Which one's better? Well, you have to look at formal charges. So let's look at the formal charges of all of them. The formal, and I'm not going to painstakingly do it step by step, but I would do it yourself to make sure you know how to do it. The formal charge on this nitrogen is, let's see, 5 minus 7. Wow, minus 2. That's a big formal charge. The formal charge on this carbon is 0. The formal charge on this, excuse me, oxygen, let's see, 6 minus 5 is plus 1. Okay, so the oxygen has a formal charge of plus 1. The nitrogen has a formal charge of minus 2. Not really good. 2 out of 3 atoms have a formal charge. Let's look at the middle structure. The nitrogen has a formal charge of, let's see, 5 minus 2, 4, 5, 6, has a formal charge of minus 1. All right, well, that's better than minus 2. Carbon still has a formal charge of 0. And the oxygen has a formal charge of, let's see, 6 minus 2, 4, 5, 6. Oh, 0. So this is a lot better, okay? 2 of the atoms have no formal charge, carbon and oxygen, and then nitrogen only has a formal charge of plus 1. So that's looking pretty good. The structure on the right, the nitrogen has a formal charge of 0. The carbon has a formal charge of 0. And the oxygen has a formal charge of minus 1. How do you now decide between the second and third Lewis structures? Because they both have the same magnitude and number of formal charges. Well, you have to look at where the formal charge is placed. This gets pretty complicated. In the far right structure, the one that ends up being preferred, the minus 1 formal charge is on the oxygen. In the middle structure, the minus 1 formal charge is on the nitrogen. So you have to make up your mind, is it better to have a negative charge over oxygen or over nitrogen? It's better to have the negative charge on the more electronegative atom. What's more electronegative, oxygen or nitrogen? Oxygen is. It's closer to fluorine, therefore it's more electronegative, therefore it can accommodate that negative charge better than nitrogen. All right, I want to talk about resonance structures for another couple of minutes. Ozone, O3, if you were to go through the steps drawing a Lewis dot structure for that, you would end up with something like this. That would make you think that you had one oxygen-oxygen double bond and one oxygen-oxygen single bond. It turns out when molecular images are taken of ozone that that's not the case. What we actually see is that both oxygen-oxygen bonds are of equivalent length and equivalent strength, okay? Whereas if one of them were a double bond and one were a single bond, they should be different strengths and different lengths. So scientists scratch their head for a minute and went, how is that possible? What happened to our double and single bond? Turns out that it's all in resonance structures. You can draw this Lewis dot structure of ozone so that the double bond is on the left or the double bond is the right. These are called equivalent resonance structures, and that means they're totally identical. There's not different atoms or different types of bonds, are exactly equivalent. And it turns out that these two equivalent resonance structures do not bounce back and forth between having the double bond on the left and the right. They exist 100% of the time as some hybrid in between these two structures. So I think this is a cool way to look at it. Just like if you crossed a German Shepherd and a Labrador, or Golden Retriever maybe, you would end up with a dog that it wouldn't wake up one day and decide to be a German Shepherd and then the next day decide to be a Golden Retriever. It would be some unique breed that is a hybrid of the two it came from. Same thing with equivalent resonance structures. It does not go back and forth between these structures. It exists 100% of the time as some 50-50 hybrid between these two. All right, we're almost done. I want to leave you with a couple of exceptions in drawing Lewis dot structures. These are the harder ones. After telling you that all atoms would like to have an octet of valence electrons, a full outer shell, I'm here to tell you now that there are several exceptions to that rule. There are three categories of exceptions. The first one is that some molecules have an odd number of electrons. And if that's the case, if you add up all of the valence electrons in the atoms in a molecule and you get an odd number, you are going to end up with one unpaired electron. So just heads up so you don't think you're doing something wrong. The second category of exception is there are some atoms that are perfectly stable with less than 8 valence electrons, and those just have to be memorized. And more frequently, there are some atoms that are perfectly able to hold more than 8 valence electrons. So we're going to go through each of those briefly. All right, probably the most common cause of an odd number of electrons is if you have a nitrogen as part of your molecule. In this case, nitrogen monoxide has 5 plus 6 equals 11 total valence electron. That's an odd number, so there's no way to get evenly paired valence electrons. So you're going to end up with that unpaired electron either on nitrogen or oxygen. And then you have to ask yourself again, okay, is one of these resonance structures preferred over the other? Well, whichever atom is missing or has a single electron, they don't have an octet. Okay, so on the left, the nitrogen doesn't have an octet, it's electron deficient. And on the right, the oxygen doesn't have an octet. Which atom do you think is more content without an octet? Nitrogen or oxygen? Turns out that nitrogen is preferred because nitrogen is less electronegative than oxygen. Oxygen is so electronegative that if you try shorting it on electrons, if you try leaving it with anything less than an octet, it is not going to be stable. All right, the two most common elements that are content with less than 8 electrons are beryllium and boron. So beryllium, believe it or not, is content with 4 valence. Boron is content with 6 valence. So please make a note to memorize those. This would be an example. So you had boron trifluoride and you tried to draw a Lewis dot structure. If you tried to force boron to have an octet like we've done in these structures, what happens is that fluorine ends up with a formal charge of +1, which will not happen. Fluorine is by far the most electronegative atom in the periodic table. No way is it ever going to have a positive charge. So immediately scientists knew that wasn't happening, and they soon discovered that boron is just as content with 6 valence electrons. So the correct Lewis dot structure for boron trifluoride is right here. So you can see the fluorides have an octet, but boron is happy with only 6. All right, and the most common exception to the octet rule, the one you'll run into most, is atoms that can expand their octet. That's the phrase, expand their octet. That means they can hold more than 8 valence electrons. So if you look at the phosphorus in this compound, PCl5, you can see that it has 2, 4, 6, 8, 10 valence electrons. That is perfectly fine for phosphorus. And it turns out that every single element that's on the third energy level, third period on the periodic table, or farther down on the periodic table, so the fourth period, the fifth period, the sixth period, all of those heavier atoms can expand their octet to hold 10, sometimes 12, and I think I've even seen occasionally 14. Phosphorus is a real common one. So the bottom line for expanding the octet is that if by expanding the octet you minimize formal charge, it's a good thing to do. Okay? So you expand an octet of the central atom when you can, if by doing so you minimize formal charge. So let's look at the Lewis dot structure for the phosphate ion, which is PO4 with a -3 charge. That's a good one to practice drawing on your own. So if you kind of push the presentation aside, get a piece of paper out and see if you could come up with the Lewis structure for a phosphate ion on your own. So you might well come up with the structure shown right here. And then if you calculate formal charge, you can see that every single atom has a formal charge. Not good. So now let's see, let's pretend what we're making, well, let's go ahead and make a double bond using one of the lone pairs on one of the oxygens. So we're going to get rid of that lone pair, and we're going to use it to make a double bond here. And now we're going to count double bonds, or we're going to count formal charges again. By doing so, we've given this oxygen that we took a lone pair from, it now has a formal charge of 0, and the phosphorus has a formal charge of 0. So we have significantly reduced formal charge by expanding the octet of phosphorus. So that is a good thing to do. Now, you might ask yourself, how many times do I need to do that? Should I try to make another double bond? You can go ahead and experiment with that, but what you'll find if you do that is that your formal charges will increase again. So it turns out this is the best structure you can make. That is it for lecture 2. And the third and last lecture is the polarity of molecules, polar versus nonpolar.